Over the past week or so, we've been talking a lot about forces, and we've talked about three big ideas up until this point. The first idea is that forces cause acceleration. Forces are the reason things change what they're doing. They can cause things to speed up, they can cause things to slow down, they can cause things to change direction, or some combination of the three. The second big idea that we talked about was this idea of inertia. Ooh, sorry about that. Inertia. There we go. No T in here. Okay. And that idea of Newton's first law, the idea of things staying the same, that whatever an object is currently doing, it's going to continue doing until it's acted on by a net force. Now that may mean it may be at rest, that may mean it's moving with a constant velocity, but whatever its current state of motion is, that's what it will continue in until we make it do something different. The third idea is this idea of Newton's second law, F equals ma, and this deals with things changing, right? That now if we have a net force, sigma F, right, and we want to find out exactly how much that motion is changing, right, A, we can do that through the relationship between net force, mass, and acceleration. These are our three big ideas. There's one force out there that really influences, especially Newton 2, but it does influence Newton 1 quite a bit as well, and that's the idea of friction. By definition, friction is a force which provides resistance to motion due to the contact between two surfaces. So a couple of things there, right? First, it's a contact force. If there is no contact, there is no friction. Like it says here, friction is by its nature an electromagnetic force. At the surface of two objects, we have some negatively charged electrons and negatively charged protons and positively charged protons and negatively charged electrons, and all of those things. There's a weird attraction repulsion going on there at the surface. The result is that there is a resistance to the motion of that object because of it. Friction is always an opposite force. It acts opposite of an applied force. It acts opposite direction of the way we're pushing on something, or it may act in the opposite direction of motion if there is no applied force. So the first thing I want to do is I'm going to show you a little video of me applying forces to an object. And we're going to look at the resistance force that's there, what it does to the object, what it doesn't do to the object, and then we'll come back and look at some data and talk about why these things are happening.
Hey everyone, welcome to Fabulous Studio 246 here. No Brittany microphone today because I got to do some things, but I wanted to show you an example of a kind of a data collection that you guys are actually going to be doing in lab next week, but I'll give you a quick rundown of it, or at least the beginnings of it here to start. What I'm going to do is when I move the camera, you're going to see I have a force sensor, new sensor that we're going to use into the lab quest next week, hooked up to a string, and that string is attached to a heavy block. What I'm going to do is I'm going to apply some forces to the block, and we're going to see some resulting changes in motion or resulting non-changes in motion. Then we're going to look at some graphs that the lab quest took and talk about what's happening there, why it's happening, and go from there. So what we'll do is I'll adjust the camera angle, we'll take this new set of data, or I'll show you the data collection, then we'll look at the graphs. Alright, bird's eye view here of the lab table in Studio 246. You see here we have the force sensor. It's just a black box. When you guys get a chance to use it, you'll see in class that it says dual range force sensor. That force sensor connected through a string to a big heavy block. This block has a couple of the masses that we use for the carts up here, then just connected through there. So what I'm going to do is I'm going to start off, and right now there's no tension in the string. So this force sensor is reading 0 newtons. It's not measuring any newtons. So what I'm going to do is I'm going to apply a small force to that block, and you see here I'm pulling a little bit, but nothing's happening. So I'm going to let it go, lose it out again. It's going to go nice and loose. Next, what's going to happen is I'm going to apply a greater force. Still no motion though. Then this third trial, what I'm going to do is I'm going to apply the greatest force, more, until finally that block starts moving and I can move it with a constant velocity. So what we'll do next is we'll look at some of the graphs that went along with that while I was making that in the LabQuest, and we'll look at what's going on there.
What I wanted to show you this time was the LabQuest, that what the data looked like while I was collecting it during the live action shot that you just saw a couple of minutes ago. So what I'm going to do here is I'm going to start up data collection, and then I'll be able to show you the screen of what the LabQuest actually looked like so we can follow the data collection, talk about it a little bit more. We'll analyze it a little bit later as we go along. So start up data collection, and I have some unsaved data, so I'm just going to discard it, and then we get started. So first thing I do is I pull out a little bit, not enough to make it go, and then it comes back down. That was a little too steep. Then I'm pulling a little bit harder. Once again, not enough to make it go. And then I'm going to pull it out a third time, a little bit harder, a little bit harder, a little bit harder, a little bit harder. Oh, then I can finally make it start going, and it ends up looking like that. Those three peaks are what we're going to use to represent these different ideas of static friction and kinetic friction, and we'll talk about that in just a second. Here's a set of data that was collected by the LabQuest during that demonstration that I just showed you before. Full disclosure, I didn't collect it at the same time as I did that demonstration before. It was collected earlier, but the ideas are the same. So notice, here we have our first peak. That was my first tug onto the object. Couldn't get it really to go anywhere, so I let it go and let it go slack. Notice our force values start off at 0. They jumped up a little bit, but then came back down to 0. Second trial, I pulled it a little bit harder. Notice this one got up to about 5 newtons, maybe a little above. This one getting up to about 7.5, maybe something along those lines. Still couldn't get it to move that object though, so I dropped it back down to 0. Then on the third time, you'll notice harder, bigger force, bigger force, bigger force, bigger force, bigger force till I hit a peak, and then boom, it drops back down to a relatively constant value. Yeah, it's kind of shaky, but that value there is remaining constant. This was the part after I got that block to start moving, and it became moving at a constant velocity. So we're going to talk about a couple of these regions and how it applies to friction. The first thing that we're going to talk about is this idea of static friction. When I first applied a force to that block and it didn't move, that is an example of what we talked about the other day in class of equilibrium, right? Equilibrium, we said, can exist in two forms. It can exist as something not moving or something moving with a constant velocity. But the important part of equilibrium is that the net force is equal to 0. So if I have that block and I'm applying a force in whatever direction, let's say it's the positive direction, if that block doesn't move, we know that that block is in equilibrium, and the net force has to be equal to 0. If I'm applying a force of 5 newtons in one direction, and I'm in equilibrium, there has to be another force in the other direction, exactly the same magnitude, but in the opposite direction, so that we end up with a net force equaling to 0. And that force we refer to as static friction. The frictional force exerted on a body that doesn't move to resist an external applied force. I applied an external applied force to that block through the string. Nothing happened. Why? Because there is a static friction force that changed in order to keep the net force on that block equal to 0. That's this first section right through here. However, again, I applied a force to that block. Again, nothing happened. Notice the force values have gotten larger. This is still a static friction force. Why? Because that block is still not moving. Therefore, the net force is still equal to 0. However, the static friction force is not a constant force. It can change with the applied force in order to keep that net force equal to 0. And that's what happened here in these first two instances. However, let's jump ahead to the third instance, right? Once again, block didn't move right away. I applied a force, 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 and all of a sudden it started moving. The static friction force adjusted itself to match my applied force to keep the net force equal to 0 until it reaches a limit. There is a maximum value to the static friction. And we refer to that as FSF max, the maximum static friction, or static friction maximum value. And here it's probably right around this point. Yeah, I know that there's this peak here, but I think that had a little bit to do with our data collection tools. There comes a point when the static friction force cannot balance out the applied force that we're putting on that object. And that's a good thing, because if static friction could indefinitely adjust itself to any force that was applied to that object, nothing would ever move. But it reaches a maximum value, and that's when things start happening. Now that that block is moving, right, this section right through here, that block is moving. But it's moving, and more importantly, with a constant velocity. We refer to that section there as kinetic friction. Why kinetic? Because it's the frictional force exerted on a moving object. Kinetic friction is a constant force. And if you notice from that graph, right, what did we see right through here? Yeah, it's kind of jumpy here, but if we put a line or took an average of this value, we'd find out that those values stay pretty constant. Kinetic friction is a constant value, as long as the object is moving and the surface stays the same. So we have two kinds of frictions that can influence the motion or the non-motion of that object. First, let me one more thing on kinetic friction. In that example that I did for you, I was trying to make that block move with a constant velocity. Once again, an example of equilibrium. Our only requirement for equilibrium is that the net force is equal to 0. So if I have a box that I'm applying a force to, F of A, an applied force, if I'm moving it at a constant velocity, that means there has to be another force in the opposite direction, granted not drawn very well. Let's see if I can straighten that out a little bit. That's a little better. There is a force being applied in the opposite direction. And if we're going to be in equilibrium where the net force is equal to 0, that means that this blue force has to be exactly equal to that green force. So in this case, kinetic friction is equal to the applied force if that box is moving with a constant velocity, which is what I was trying to do in that example. All right, so we've talked about two different kinds of friction. Static friction keeps things from ever moving in the first place. But if we get to a maximum value, we then transfer over into kinetic friction, and that handles the moving part. If we take a look at this graph down at the bottom, this is an ideal situation, but it's illustrated in the graphs that we took with our lab quest. You'll notice that on the lab quest, the x-axis here is time. That's not the case, time, there it is. That's not the case in the graph that's down at the bottom. Notice that the x-axis is applied force. I don't have a way to measure both of those. Actually, I probably could if I rigged something up, but we get the point just in case. On the y-axis of both graphs, we have force, and more specifically, frictional force. So if you notice during this section of the graph down at the bottom, the ideal graph, right, during this section that's being highlighted yellow right now, the frictional force is increasing as the applied force is increasing. I know that if you took the slope of this section of the graph, it would have to be equal to 1. Why? Because if this is the static region, as it's saying here on our graph, if no motion is occurring, that means that there has to be an equal amount of applied force and frictional force. If you have a line that's going up by the same amount each time it's going over, rise over run, that slope is equal to 1. So the slope during this section is equal to 1 because the frictional force and the applied force are balancing each other out until we reach this point right here. All right, let's give it a star. We have hit the maximum static friction value that is available between that object and that surface. Now, our frictional force dives down and becomes a constant value. We have entered the kinetic region. The kinetic region implying that that object is moving. Notice that the frictional force remains constant through this section right here. However, on this graph, the applied force being measured on the x-axis keeps getting larger as the frictional force remains constant. So in the bottom graph, we have an object that is accelerating in any point past this maximum static friction value because there's more applied force than kinetic friction force. However, if we look at the graph that the LabQuest took, let's bring this to the front, okay? This frictional force is remaining constant as y applied force was being constant. So in that case, we had equilibrium of constant velocity. But in this case, here, we have an object that is accelerating because the applied force is greater than the kinetic friction. However, we both see this pattern in both graphs where at the beginning the frictional force increases till it reaches a maximum value, drops down, and then becomes constant. Now that we've talked about the different kinds of friction that exist and how it applies to an object in motion, an object not in motion, let's talk a little bit more about, static versus kinetic friction. The maximum static friction value is always going to be larger than the kinetic friction value if we're talking about the same object on the same surface. It's easier to push a heavy object once it's already moving. It's hard to get something to start moving, or harder to get something to start moving, than it is to keep it moving once it already is. Now that we know about those different kinds of friction, let's discuss what's determining the frictional force for us. It depends on two things. How much friction, and this goes for both static and kinetic. How much friction and force there is depends on two things. It depends on the surfaces that are involved. So the composition and the smoothness of the surfaces. But the other thing that it depends on is the normal force, F of n. Okay? A new force that we haven't been introduced to, but it still does the same thing, still causes acceleration, etc., etc., etc. A concept that we were introduced to yesterday, or Monday in class, was this one, the force of gravity, F of g. And we said another way to describe F of g is the weight of that object. We talked about that F of g is calculated by doing m times g, the mass of, in this case, this adorable cat wearing a bow tie, the mass of that adorable cat times 9.81, which is the acceleration caused by gravity. However, if this adorable cat is sitting on a table, it's not accelerating in the up and down direction. That means the forces in the up and down direction have to be balanced. This object is in equilibrium, right? Once again, net force equaling 0. That means that the gravitational force downward, the weight of this object, must be balanced out by some other force. In this case, we refer to it as the normal force. Normal force is a support force that is exerted on an object by a surface perpendicular to that surface. That's where it gets its name, the normal force. Normal is like an old school way of saying perpendicular. Like it says here, F of n is always perpendicular to the surface, regardless of the angle of that surface. That's going to come into play a little bit later in the year when we start talking about inclined planes and objects rolling down hills and stuff like that. But for now, stationary object, F of n, almost always, not always, but almost always, is going to balance out gravity so that F of the net force is equal to 0. That creates an equilibrium situation and no acceleration occurs, at least here in the y dimension or the up and down dimension. Okay? So a lot of times the normal force is equal to the force of gravity, but not always. That normal force goes into determining what the actual value of friction is going to be through something that we refer to as the coefficient of friction. Coefficient of friction is symbolized by this Greek letter mu. It looks like a U with a tail on it. Freehand, I draw mine, it kind of looks like this. The coefficient of friction, like it says here, summarizes the contributors to friction. It allows us to determine how much frictional force is actually acting on this object. The coefficient of friction is equal to the force of friction divided by the normal force. you're looking at the coefficient of kinetic friction. However, there's also a coefficient of static friction, mu sub SF. The coefficient of static friction is still equal to a frictional force, but this time it's a static friction force, and more specifically, the maximum static friction force divided by the normal force. The mu value does not show up on a free body diagram. It doesn't show up in the problem, but it does allow us to calculate how much frictional force actually exists in a situation so that we can then make predictions about what's going to happen, when is this object going to move, how can I move it with a constant velocity, etc., etc., etc. If you look at the formula for coefficient of friction, you're taking a force in the numerator, dividing it by a force in the denominator. If you look at the units, force in the numerator is going to be measured in newtons, because that's what force is measured in. Force in the denominator, also going to be measured in newtons. If you have newtons over newtons, those units will cancel, and there is no unit on the coefficient of friction, because it's a ratio of forces. It's telling you how one force compares to another force. Specifically in this case, the force of kinetic friction, or the force of static friction maximum, to the normal force itself. So the coefficient has no unit, but we can use it to calculate the force of friction. If we do that, that will have a unit of newtons. So that sums up this idea of friction and introduces you to a couple of concepts: static friction, kinetic friction, coefficients of friction, and then the normal force. We're going to use those in class, do problems, analyze situations over the next couple of days, see how it influences both Newton's first law and Newton's second law.